Hi everybody, welcome to this tutorial. We are going to focus on generative classifications, basically on naive Bayes, and we want to consider this technique, very strong technique. Also, we want to consider mathematics to see how does it work, and we will focus on Gaussian Naive Bayes. All right. And then the second part, I will take you to the coding part and the live session. And we want to use machine learning library on PySpark to see how we are able to use the Gaussian naive Bayes on big data analytics. And of course, optimization. We want to consider how we are able to optimize naive Bayes. So let's go through this. To be able to work around with this generative classifier, basically we need to, like, as a recap, we need to remember what type of classification we have. So the first one, we call it discriminative classifications, that they draw boundaries like this in the data space. And these discriminative classifiers focus on learning this decision boundary, right? I'm talking about this one, that separate different classes directly. This is what exactly we, expect from this sort of classification, like logistic regression, that whenever we discuss about logistic regression to provide, these are class 0 and this is class 1, this S shape, this is exactly the boundary, right? That we would say these are all belonging to class 1 and these are all belonging to class 0. Or if you're familiar with support vector machine, decision trees, random forest, these are all into this family, that we would like to get them into this format. But whenever we talk about generative try to model how data is placed throughout the space. All right, so it means it's working based on probabilities. Speaking, generative classifiers model the probability distribution of both the input features and the class label. So like naive Bayes that we want to discuss. So it means that generative algorithm work on probabilities. That's going to make classifications more strong and more accurate, more robust comparing to discriminative algorithm. So let's drill down more, all right, to see what they will be. So naive Bayes is a classification algorithm based on Bayes theorem with the assumption of independence between features. All right, it comes exactly from this keyword that we call naive. All right, so we can use this naive Bayes for many classification problem, like text classification, spam and recommendation system for intrusion detection, and many classification problem. Because of using probabilities, it's going to make modeling very strong. And few things about this naive Bayes is basically there is no training because it's based on probabilities. So we want to discuss shortly. And one more thing about naive Bayes is you can if you're looking for a strong classification to be able to work ideally on small size data, right, and huge size data, usually naive Bayes can work really great in both cases. All right, so this is what we expect from naive Bayes, right? So naive Bayes, there are, guys, few keywords we need to follow up. So let me see. Let's start from this one. Probability of C given that X. So we call it posterior probability of class C given the observed features X, right? So in the context of Bayesian statistics, this posterior probability refer to the probability of a hypothesis or events occurring, guys, after taking into consideration new evidence of information. All right, so it means that this is essential in making informed decision and updating beliefs based on new data, right? This is really great because this is what we expect from probabilities. So the second one I want to take over is here, PC, right? The probability of C. So guys, here let's take C as a class. Means that if you have like the binary problem, right? C here would be class 0 and class 1, right? And then X gonna be your data point, your features, let's say. So yeah, it's better to call X features. All right. So C is gonna be, you know, your classifiers, and X would be your features. All right. So PC here, we call it prior probability. So prior probability means the initial guess, right? The initial guess that also is here is mentioned in this represent the probability of the class label C being true without considering any specific features. Exactly, we call it initial guess. What does it mean? It means that if you have 100 data point, 50 class 0, 50 class 1, and then we call it 50% is going to be P, you know, class 0, and the probability of being class 1 is going to be 50%. If you have 100 data, that 70 belongs to class 0, right? And then you would say that PC0 is going to be 70%, right? This is initial guess without considering any specific features. All right. So this one, PXC, is the likelihood of observing the feature value X given class C. This is very important for us because we need to know how we can calculate it. So there are different naive Bayes techniques that we can take them into consideration, right? For I mean, for modeling and for let's say for calculation, that this one, in this case, we want to calculate and we want to go through Gaussian naive Bayes, and we will discuss shortly that what is and how we can take it over. The last one is PX, so it's going to be here, you can see that. So is the probability of observing the feature X regardless of the class label. It means, guys, normalization. So it means that for Px, you need to go over the probability of each X and consider, is X belong to class, let's say class 0 multiplied by the initial guess that we did here, right? Again, you have to do with second class, third class, fourth class. Why? Because you want to collect all together, make a summation, right? And divide, you know, just, you know, and divide, you know, this let me change the color. So then you can, you know, calculate this and divide it by normalization. All right. So this is what we expect from naive Bayes. But in this case, we need to firstly go through this one and see how we can find it out. And taking mathematics, right, numerical example, is going to really make it easy for us. So guys, there are different type of naive Bayes that I mean, in this tutorial, we're going to take Gaussian naive Bayes. That is really great for continuous features. All right, if you have data set that your data mostly based on continuous data, Gaussian and naive Bayes is the best choice. If your data is more based on categorical data, all right, categorical, either numerical or textual. Let's say you have column called sex is going to be male and female. This is one categorical. You have, let's say, you have might be the salary, but the salary is in the scale, like class A, class 1, class 2, class 3, for instance, for salary, still categorical. It means that if your data is based on categories, we can work with categorical naive Bayes. If your data set is based on Boolean values, Bernoulli naive Bayes. If your data set is based on discrete features, all right, multinomial is going to be really the great choice. and usually we use this multinomial naive Bayes classifier for document classification. Document classification, or let's say for finding spam or non-spam emails. Because in the email we have text, right? We need to count the words, and based on those words, that counting is distinct. Like for instance, if you say hi friend, might be in the message you have 8 friends written, right? Maybe you have 2 word hi and other words that you have to count. So since this is district, I mean, we can use multinomial. That's the reason naive Bayes, in particular, multinomial technique is really great for text classification, right? So, and also complement naive Bayes. So complement naive Bayes is perfect for imbalanced data. All right, means skewed data. All right, let's say if your data is 90% class 0 and 10% class 1 is, you know, the big imbalance, right? And then we can go ahead with complement. But in this tutorial, I'm going to take you to Gaussian one. Really a great technique, because we usually use Gaussian for, let's say, for classification purpose. So how does it work? So Gaussian naive Bayes. So what we expect is this one. All right. So this is the way we have to calculate this probability. All right. So how does it work, guys? This is exactly the formula of Gaussian distribution. So in this Gaussian distribution formula, we need this one. Let's call it mu, which is the mean. So mean is here, means that every single data point subtract by the mean, but they should belong to, you know, the class, right? Every time, you know, belonging to class. Let's say class 0, once to class 0, then to class 1, then to class 3, right? And then we can calculate. And then variance, we need to also calculate variance. Variance is here, right? This is the variance. This is the variance that we have to calculate. And pi, right? Also pi is here, right? Constant value and exponential, right? Means e that we can take over, and this is the Gaussian. So, all right, okay. The question is, okay, how we can apply all this stuff together for Gaussian naive Bayes. So let me take you to example and make it really easy to, how does it work? Let's say we have 4 data points, all right? So 2 data points belong to class 0 and 2 others belong to class 1. So let's go through calculation. So what we need to calculate, guys, let me tell you what we need to calculate firstly. So first of all, if we get back here, all right, so maybe we need to do something like this. All right, because we need this, we need to get back to this one. All right, first of all, why not to calculate this one? Prior probability. So if you remember, we said that this represents the probability of the class label C being true without considering any specific feature. So it means that if you come down, so exactly 2 out of 4, and also these 2 out of 4 means exactly 50% for this class 0 and 50% for this class 1, right? It means the probability of class 0 is 50% and probability of class 1 is 50%. Prior probability. All right, one is done. So the second one is calculate the class conditional probabilities. This one. All right, P X I, given that class C. So if we get back to this formula, to this one, we are going to calculate this one now. All right, so how we calculate? We said that the problem is Gaussian naive Bayes. So the Gaussian naive Bayes means that we need to calculate this one. All right, so in this case, what we need these two, the average and variance. We need to know how to calculate both. So we need to come down here. All right, so you can see that for X1, so basically, guys, we need to do class by class. For class 0, All right. We have three features, right? You have to go through each feature. Now feature X1. So for each, for X1, we have 20.2 plus 14 divided by 2. Why? Because guys, data point is here, right? 20.2 plus 14 divided by 2, just X1, right? Because these are only belonging to class 0. And then we need to repeat for this and repeat for this to calculate the average. For class 0, we do the same thing for class 1. And again, do the same thing for variance calculation for class 1 on each feature separately. And then same for class 1. All right, all the stuff we do. So calculate the average. It's going to be this one. So, the variance. All right, the variance, you can see that it's going to be the value subtract by the average power 2 plus the value, right? Means X, right? The second column, second feature, subtract by the average power 2 divided by 2, and we call it variance. All right, same we can see that we do for all three features belonging to class 0. We repeat this stuff to do for class 1, right? Again, the average of X1, the feature X1 was 2.1 plus 4.8. So it's going to be here, right? These two now. All right, and then we do same as we did for class 0. All right, we did do all the stuff, and then it's over, right? All calculation done. What we need to do from now on, we have to find, this. We have to calculate, we have to calculate now this one. All right, this is based on new evidence, new data, because new data comes over, we need to find which class belongs to. All right, so guys, this px, as I mentioned, you can calculate this as we did here, as we did for this one and this one, right on top. But since this take the idea of normalization for this, live session, we can, we can ignore. But by the way, you can calculate this px for for this naive Bayes. So let's go through this one now. Okay, new data comes over, we want to find which class it's belonging to. So how to check that? So let's say we get new data 20.2, right? This is x1, x2, and x3. All right, and now we want to predict what is the label. All right, since here we have 0 or 1, we have to check, is it 0 or 1? So how to do so, guys? We have to go through firstly class 0. All right, and calculate these Gaussian Naive Bayes. So Gaussian Naive Bayes says that for px given that belonging to class 0, all right, it's going to be 1 divided by 2. P multiplied by 7.82. So what is this 7.82, guys? If we get back here, all right, you can see that this is a variance of class 0, right? We have to take it class by class. All right, so and then we have to calculate this, and to find, the probability of, if I come down, all right, and then you can find the probability of x1, feature 1, means this one, 20.2, given that belongs to class 0, you have to calculate, this is the probability. You have to repeat for, for feature 2, for feature 3, and these are all for class 0. And then you have to calculate this probability for class 1. All right, and you can see, you can find, everything as we need here. Finally, calculate the posterior probability. So guys, posterior probability, it means that PC0 given that x1, x2, x3, because now we have to check which class. You have to interpret like this: which class given that we have x1, x2, x3. So this one, all right, is exactly this formula that we took over, right? We are exactly talk about this one. But here we have just considering one feature, but in reality that we are working with, we have three features. It means that the multiplication of this P, the probability of the class, multiplied by all probabilities that we calculated by Gaussian naive Bayes, all right, and divided by normalization. I said that for this live lecture, we can ignore it, but then if you wish, you can calculate also that normalization. So then it would say that P C0 multiplied by Px given that belong to class 0, P the probability of x2 given that belong to class 0, and then probability of x3 means third feature belong to class 0. All right, and then you can calculate. So how we got them? So you just need that. So we got this prior one, 50%. All right, and then you know this one we got from this one, right? So this one you can take them and bring them here, and then this is the calculation, and then you can do a same thing for class 1, and then it's going to be very close to 0. So since the posterior probability for class 0, I'm talking about this, is greater than this, all right, we classify the first instance belongs to class 0. All right, you can see that using probabilities, you can find the classifier for new data. There is training. You can see, guys, there is no specific training. Training means you need to take data, you need to get like the number of iteration, take your algorithm, go through algorithm, tune parameters, or move your your straight line or that curved line, that we discussed, for logistic regression. There is no particular training, so just probabilities. So there is a limitation of this naive Bayes, means zero count. All right, if the probability for a value of one feature is 0, right? I'm talking about, let's say if for the probability of feature 2, all right, the given class, let's say class 1, let's consider, for instance, let's consider this one. If it's 0, all right, it's going to affect negatively on this calculation. It's gonna be make it 0. All right, so we don't have 0. All right, because otherwise it's going to mess up this probability calculation. All right, what is the solution? We can add a minor value to each count. All right, and then we call it smoothing. And this is smoothing, ensure that we don't have 0 probabilities. All right, so guys, this is all about this Gaussian distribution. All right, and if you want to take it on mathematics, that how does it work? But I wish to make it even much easier for you to understand how does it work. Since we have 3 features, and then you can have something like this, guys. You can take it like as the second solution of consideration on this Gaussian distribution to think even much better, right? To avoid this mathematics and come over here, right, and calculate what's going on. Let's say that this is for attribute 1, attribute 2, and attribute 3. So for each attribute, you can draw a Gaussian distribution. What is Gaussian distribution, guys? Gaussian distribution or normal distribution means that you need to collect the average and the standard deviation and draw a Gaussian distribution. All right, how data, it means that how data were spread out, right, across the mean average by the consideration of a standard deviation. Let's say that for I mean x1, for feature 1, if you consider class 0, all right, let me come back here. Here we have we have 2 data points. Let's call each data point, each class we have 10 data points, all right, for class 0, and let's say 20 might be, or 10 again data point for class 1. It means that then we have to go through all class 1, all x1 and calculate the average, all right, and the standard deviation. All right, this is what we did here, right? We did it, guys, here, right? We did here. All right, calculate it, and based on that standard deviation and average, you can find the Gaussian distribution. Let's say the Gaussian distribution would be something like this for class 0. All right, so for feature 2, we do the same thing, and let's say might be this one is going to come up with something like this. All right, this is class 0. For feature 3, also we do might be it's come, with very short, right, class 0. All right, so and then now for class 1. For class 1, we do the same thing. Come over here, go over class 1, calculate mean and standard deviation, and then you are able to find this distribution. Let's say distribution here is going to be this one. All right, this is for class 1. Here we have this one. Let's say this is class 1, and maybe this is very tall, and this is class 1. All right, so distribution. All right, and we already know that this prior P, the probability of class C is 0 is 50%. Let's say we have exactly the same number of the same number of records for both, right? And also 50%. So then new data comes over. So new data comes over. Let's say that for new data, we have x1, let's say is 20, for instance. You can find 20 is here. All right, and then the second one is 10. Let's say it might be 10 is here. All right, and for third one maybe is 100. Might be 100 is here, for instance. All right, these are new data comes over. So that then we have to calculate, the naive Bayes. The naive Bayes says that P, right, class belonging to 0 multiplied by the probability of, right, the value x1 is 20, given that the class is 0 multiplied by the probability of, now this one, x2 is 10, given that class is 0. All right, multiplied by P, x3 is 100. All right, given that class is 0. We have to calculate this. How to calculate, guys, this one? So we did it, right? We did it here. Yeah, I'm talking about this one. You have to calculate this stuff. For first one, you need to calculate this. All right, so it means that for this, all right, x is 20. All right, you just need to go through, oh, sorry about that. You just need to come over, this formula. So sorry, guys, I'm just, okay. You need to come over here. All right, so then you need to calculate this Gaussian one. So how we know that the data we have, the value we have is 20, right? So we know pi 3.14, right? So you did calculation on variance, which is also standard deviation, or let's better to call, variance, and then the average. All right, and then also again the variance here, and then we can calculate this one. Once you calculate this one, you come back here. Maybe for this one, all right, maybe after the calculation, this one would be let's say 0.6. All right, and this one is 0.5, right? Because of this one. Maybe this one you got it, 0.7. Maybe for this one you got it I don't know, let's say 0.1, for instance, and then you get the value. You need to do the same thing for class 1, and which one is bigger, larger, you can take it as the class. All right, this is the discussion that how we can take over this Gaussian distribution. I hope you enjoy, guys, this topic. Very important classification topic and discussion. And next part, I'm going to take you to machine learning library on PySpark to see how we are able to use this naive Bayes into practice for huge size data. Welcome back, everyone, to part 2. We are going to go through Gaussian Naive Bayes classification in PySpark machine learning with optimization insights. So let's kick off and let's go through these steps. So guys, first of all, we need to install PySpark since we are on Google Colab. So guys, please make sure to download this file, which is source file, from the course page or from the description of this video to be able to work around with this IPYMB file. So in this cell, we need to import few packages, libraries, and then we need to initialize a Spark. And I mean, with a few configuration that we discussed about this configuration in previous videos. Please refer to our previous videos about how to work with data frame and how to master data frame in PySpark. So then you need to load data, basically data in this tutorial would be based on KDDCup. Guys, make sure to have your drive mounted. So I've already permitted this access to my Google Drive, so that's the reason it's not going to repeat it. It says drive already mounted, but might be for you, it's going to get permission, and you need to accept the permission for this mounting. So then you need to download one of these files. So the entire file, let's say the whole data, 700 megabyte uncompressed. It means that if you download this data, it's 18 megabyte because this is a zip file. And we want to work with this 10% subset, which is 75 megabyte uncompressed, but it's going to be 2 megabyte. Guys, this is really great feature. The Spark is able to read even zip file. All right, so please make sure to download one of these and then place them into Google Drive because we need to read these data. And then here I'm taking 10% data. That's how we can work around. So if you're not familiar with data, as you know that for data engineering job, for machine learning task, we need to get familiar with data firstly. So the URL to know what is this KDDCup. So KDDCup dataset contain network intrusion detection data is a historical data that there was an algorithm that this algorithm collected different traffics, both normal and abnormal, that we call it unauthorized access or malicious traffic. So we have this data. Basically, we use this data for anomaly detection and intrusion detection systems. And for this task is also we want to use this one. If you are familiar with network traffic, with virus, with network intrusion, that's really perfect because you can go through these features and data description and get familiar with this data. If you are not interested in, if this is not your background, still you don't need to panic because the task here is having a multi-dimensional data like this KDDCup with 41 features that we want to predict a label. What is this label? Traffic or attack, or 1 or 0. Let's say 1 means normal traffic, for instance, 0 means attack traffic. Or let's say spam, non-spam means, or let's say true or false. I mean, just imagine we want to, or task here is prediction, or regardless of where we collected this data. So let's go through this data. Since we are working with Google Colab and we have just 2 cores available in the free version that we are using, and speed up, every single processing here on this live coding, I'm taking this data 10%. It's going to be 75 megabytes. So here I'm going to load it. So guys, make sure to get your data in your drive and my drive. If I go through this one, this is my drive, and in the file folder, you can see that here I have this KDDCup 10%. And if you click on these 3 dots and then copy passes here, and then you just need to copy and paste it here, right? And then you can get your data for reading. So I'm going to say show 5 because I want to make sure that data is there. So header false means as I know that this data is like a plain data, there is no header. That's the reason I would say, okay, there is no header. Take first row, right, as the first record, not as the header. So, and the problem here is while Spark reading zip file, Spark cannot take optimization on the number of partitions. That's the reason whenever you read a zip file, Spark, regardless of the size of the zip file, is going to take it into one partition. It means if you read this one, it's going to put all into one partition. If Spark reads this one, still one partition. So guys, be very careful, right, about zip file. If you have a zip file, make sure after this partitioning would be automatically by Spark, make sure to repartition it. So here we have about 500 record, one partition, as I mentioned, Spark, because this is zip file, Spark cannot repartition it. So you can see that these are the header because there is no header. We said header is false, and it took random header from C0 to C41, right? You can see that the last one is the label, which is the column label, right? That we want to predict this one because this is the dependent variable and the rest is independent variable. So if you wish, you can say that you can repartition it. df dot repartition, please, for me. Repartition. So let's take 2 partition, I think, because it's going to be 75 megabyte, right? Each partition in based on split into 2 is going to be 36, something like that, 36 megabytes. So let's double check that get number of partitions. All right, to make sure we have 2 partitions, and about 35 megabyte each partition is really great. So then we need to rename the column because we want to see what labels are based on data description, that you can go through this labels or whatever. You can go through this data description, you can find out about this column label, and then here we do have all this renaming. All right, so then the show 5 to just make sure we have all get renamed. So after this, let's check the labels. All right, perfect, guys. Can see that the column labels, we have them now here. If we go to the last one is the connection status, that because here we rename it to connection status, and we want to get familiar with this because this is the classification we want to do, right? That's the column we want to have prediction. So to do so, let's say that please data frame select for me this connection. If you press Control, let me type it, connection. So status, okay, the last column. So please give me distinct, all right, distinct, and show me like 30. Shouldn't be more than 30 features here. Oh, sorry, not more than 30 labels here. And you can see that these are the name of the labels. So in the logistic regression lesson, if you haven't watched that, please refer to that logistic regression lesson that we used logistic regression for binary classification. And what we did, we took normal and we converted to 0. And for the rest, right, we took them 1, means we rename them, right, to all to number 1 because we wanted to consider them all attack, right? 0 and 1 means binary, but here we want to keep them because we want to do multi-label classification or multi-class label classification. All right, so let's count them for our information, right? Let's count the labels. Let's see that how many there are. So if you want to count, you need to group by, right? You need to group by based on what? Based on this connection status. the last column. So please count them and then order. Let me also order by, because I want to see how many there are based on this order, based on count column, because whenever you order it based on this aggregator, which is count, you can see that the column will be automatically there, that it's going to be count because of this count, right? That's the reason count is the label. And then our ascending false means put it into the descending format, please, for me, and show. All right, and show all together for me. Great. So can you see that? So Smurf attack traffic is the highest, population here. So Neptune, another attack, the second rank. So normal traffic is the third rank. So, and you can see that back and nmap pod guest password, these are the number of records, like there are 53 records, right, including guest password attack. So, and the last one, multi-hop, which is there are 7 records. Again, guys, folks, if you're not familiar with these labels, with the attacks, don't worry. Just take them like as the label. Let's say these are for healthcare. Let's say these are for weather forecasting. Let's say these are for finance, right? Let's consider it from somewhere that we are not expert, but at least we know that there are many labels that our task is to predict them, right? To classify them. So if you have the minimum number of attendees here for this, connection status or attack, so they might be as outlier, right? Basically for this, because the rest, or maybe these are somehow outliers because like the minimum number of records there are. But this is good here. This is going to be really good practice. Why? Because we want to use a model like Naive Bayes. We want to make sure it's robust against even with the labels that having the minimum records, right? Let's say that if you are able to find a classifier that can classify this data with higher accuracy in presence of the lower number of, or let's say the small number of records for these attacks, or let's say these labels, and the highest number of attacks or traffic, for these ones, it means that's going to be really perfect model. All right, that's the reason we are not going to drop them. We want to keep them to see what we do. So the problem here is we need to convert them to numbers. All right, because for prediction, mostly, let's say machine learning algorithm require the label column to be numeric. All right, so in this case, what we can do, we can use this string indexer to map labels. Let's say to map labels to indices. All right, indexes, let's say. Indexer, please, a string indexer. Please get which column? Input column. Please get this connection status. All right, and then output. So output column. Which one? Let's call it label. Let's take it easy and label. So indexer, please fit to this data frame, and then apply all the learning you got from fitting to data frame, and then overwrite it on data frame. All right, so then let's run it. All right, and then here, what we did here, I mean this one, right? Let me copy this one, the group by. Let's come back here, and let's say not connection label. That's it. All right, and then run. All right, perfect. So can you see that label 0 is now a smurf? We can see that exactly the same number of count here, right? Because we didn't touch count, we just changed the label. So label 1, right? Label 1 is so label 1 is Neptune, and normal, which is or normal traffic means there is no attack, is gonna be our label number 2. So guys, it really doesn't matter. It's level 1, level 5, level 3, right? Just this indexing is important to make sure we have this indexing. So how many labels? 20 labels. So guys, this is multi-label classification. All right. So great. So here we need to, I mean, this string indexer that we apply for label, we need to apply it, guys, still on other columns that they are still textual columns, like for protocol type, service, and flag. All right, let's do for these three. So let me copy this tree, Control C, and come over here. So before vector assembler, let's say that. Let's here say string indexer for other features that they are categorical. All right. So let's say columns to index. All right, let's get all together these three features. You might have more than three features. Instead of repeating an action, you can write a loop and apply the loop on all columns that you need. In this case, it's going to be just three columns. So for column in this column to index, all right, please, what to do? Apply this indexer. So indexer, let me copy this one. All right, and come back here. So this one input index should be this column, right? And output column, again, gonna be this column plus, let's rename it, right? Let's say, let's call it indexed, something like this. And then this one. Go to next line, apply this, and done, right? df.show to make sure we did everything accordingly. All right, if we go right side, perfect. You'll see that protocol type, service index, platinum index. Okay, we could convert them. So out of this, we need to get rid of this. This is a textual column. We don't need that because for machine learning, we don't need it, right? We have label here, right? And we want to use label. So that is one column, the rest number, number, number. So then these three, because we could convert them to number. Let's get rid of, this column, and we can name it something like this, that drop unnecessary features. So what features? Let's say exclude columns. All right, let's call, and of course this one duration, which is the timing, right? We don't need that. The timestamp, right, is going to be timestamp. So I copied and I'm pasting here. So duration. So protocol type, right? This is the list of columns that we don't need them. So flag, and last one, connection status. All right, connection status, done. So now let's write, let's say that we would say that for column in df.columns. All right, we have to go through all the columns. All right, if column not in this exclude, or maybe it's gonna be like the hierarchy of these conditions, for loop, and then if condition, and then else condition. So you can take it much easier. So I really recommend that, to do something like the advanced consideration on for loop, that really senior engineers and developers, they usually do. So I want to do like this. For column in data frame columns, I want to put them in front of each other. If call not in exclude column. All right, so do nothing, otherwise return column. All right, this is what we learn to do. Input column would be this one, collect them as a list, and that's it, right? As I want to say the df, please, you want to be this df, but with these columns. All right, let me say df.show 5 or maybe 2. All right, to make sure we could drop those unnecessary columns. All right, great. Can you see that? Now, those unnecessary column at the beginning, they are gone. I mean, this one, and connection status, you can see that connection also is gone. It was before label. Okay, great, perfect. So now we have to go through vector assembler. Prepare the features column. It means that you need to collect every single record into a list, right? Into a single vector column. So how to do so? So before doing so, we need to make sure that the columns, they are numbered, not a string. So you can check df. All right, df dot print schema. If I do run it, so guys can see that these are a string, right? Except these 4 that we did them, right? We made them. All right. So what to do? We need to convert the type of the column. So let me go through this library, PySpark SQL functions, and then get this column. All right. Package. Why? Because of this loop. For column in data frame dot columns. Please go over each column. All right. And df dot with column. All right, with column means that go through the column. Which column? So if you say just column, all right, you get error because you need to also get this call, this one, to say that, all right, this column is a Spark based data frame, means we need to have parallel processing. So dot cast. Cast means convert the type to double, whatever it is, convert to double. All right. And then make sure to keep it as the column name, right? Rename it as column name. So then overwrite it on the data frame. All right. So then if you want to make sure everything is as it is, so you can come back here. All right. Or maybe let me copy this one. All right. And then you can come back here and code run again. Great. Can you see that? Double, double, double. Every column is double. Perfect. This is what we really needed. Then you can do, vector assembler. So for vector assembler, we need to apply it over all column except label. You need to exclude it. All right. How to exclude label? Again, you can write a for loop, say for column, right? In df dot columns. All right. If column is not labeled, all right. If it's not labeled, please return it. All right. Please return it. Okay. And then here we need to collect them all into a list because this is a one single for loop. I want to say that features, these are features columns, all right, not including the label is not included. All right, so here then here I want to say that create a vector similar, right, to let's say with all input features. All right, so to create a vector input, right, guys, we are discussing from this part, right? Prepare the featured column because we want to have a single vector column. All right, for training. So assembler, please, I need a vector assembler. All right, what to do? Input column, input columns, because there are many columns. We have to say input columns. I need this one. What is the output column? So I need one column, all right, on output column. Output column, please take, features, means created for me. So then data, please collect this one, assembler dot transform this vector assembler over data frame. That's it. And if you want to make sure that everything is as it is, so let me select data frame. So from now on, we want this feature only and label that we didn't touch it, right? So please overwrite them onto the data, and data, please show everything to me. 5 records enough. All right, truncate false means do not cut off the lines and then show me as many there are, and you can all right, seems there is error. So all right, sorry, this is features, all right, because of these features. All right, let me run again. All right, as you can see that this is the output, so a bit difference. So we call it a sparse vector. So this is the compact representation that is store only non-zero elements, because this data set, guys, we are working with KDDCOP has many zero values. This is really a great feature and a really advantage here when dealing with high dimensional data where most elements are zero. So this 40 means the size of the vector, this 40 means the size of the vector, and these numbers you can see here 0, 1, 18, 19 represent the indexes of the non-zero elements, guys. All right, it means that index 0, index 1, index 18, 19, they are non-zero. What are the values? These are the values. All right, this is the way that you can represent data, this view. So afterwards, what we need to do, we need to have normalization, or this idea of standardization. So what basically we need to know, guys, usually we mix up these two concepts. So but these are different. So why they're different? Normalization, we use it to scale the value basically between 0 and 1. All right. So why we need this normalization and standardization? To ensure that the features are on the same scale. This is, guys, super important in machine learning because we can avoid the impact of variables with larger scale, right? And this is really important for us to do normalization or standardization. So normalization, like MinMaxScaler, is the technique that you can use for normalization, get your input between 0 and 1, or this technique, a standardization, that involve transforming the value of a feature to have zero mean and unit variance, like StandardScaler, which try to get your input between, to keep your data between the average, let's say 0, all right, and the standard deviation of 1. How does it work? It says that get each value, subtract by the average, all right, divided by a standard deviation. This is the way you can do this standardization. So but of course we have some other techniques here, like robust scaler, that we usually use it if you want to have a robust classifier against outlier. If you believe there is outlier in your data, if you know how to find outlier, that's perfect. But if you guess there is outlier, but if you're not sure there is outlier, so you can use robust scaler, or you can use these three techniques, all right, and then see which one's going to provide basically better results for you. So if you want to use, let's say, standard scaler, you just need to say scaler, please get this standard scaler for me. All right, input column, so features would be input columns. What about output column? So output column should be, from now on, we want to name it the scale features. All right, that's it, right? This is the standard scaler. If you want to get, this min max, you just need to come over here, copy this one, paste it here, and this is standard, name it min max scaler. All right, that's it. Or if you want to use this robust scaler, all right, robust scaler is going to be, let's say, robust against outliers. So let me copy this, and instead of you have to say robust scaler. Or you need to use one of these techniques. All right, let me, in this live coding, let me use third one. All right, so feel free to use one of these three, and the scaler now gonna to fit over data, and we want to name it scalar model, something like this. All right, and then what else? Let's say data is gonna be this scalar model dot transform, means applied on after learning all after learning all the required features, please transform it. So you might ask how this robust scalar work, because we know that it works based on average standard deviation, it works based on minimum and maximum. How? This standard scalar says that value subtract by the average of the total values is going to apply over each column, right? And then divided by standard deviation. Min max, it's going to say that x subtract the minimum of the value, all right, and then divided by max divided by max subtract by min. All right, so, and robust scalar is going to be this x subtract by the median, means the middle value, divided by interquartile range. So you can see that, guys, the concept is a bit different. So it means that this might be, you want to ask me, what is this IQR? It's going to be the quartile 3 subtract by quartile 1. All right. And then the median means the middle value. All right. And then you can calculate the robust scalar. So then once you apply one of these, let's see what will be there. Let me just select what to select. Please just let me select these scale features. All right. So, and then the label, and just show me what's going on here, right? DF, please show just 3 records and truncate false to make sure everything is visible without truncating the output. So again, guys, it's up to you which one you prefer to use, but we assume that we have outlier. All right, if you are sure there is outlier, if you know how to find outlier, and this is really great one that you can avoid outliers, and then this normalization, or let's call standardization, helps to scale your data under the consideration of outliers. So there is error. Let me see. So robust scalar input column. So output column scalar model is scalar. So that big data. Sorry guys, I missed S, right? Transform. And if I run again, all right, so you can see that, guys, these are non-zero indexes, and you can see that these are the values, right? These are the values after normalization, but here let's call it standardization, right? Because we didn't use normalization. So that's it. Perfect. So now we can go for data splitting to have training and testing data. So I want to say that data, please, random split. All right. So as usual, 70% training, 30% testing. Why not to get this seed? 1, 2, 3, 4. So guys, this seed is a number that initializes the selection of numbers by a random number generator. So, but let's say that by giving the same seed number here, 1, 2, 3, 4, a random number generator will generate the same series of random numbers each time a simulation is run. All right. If you want it, you can take it over. So please do so and get the first 70% to train data for me and the second one into the test data for me. All right. That's it. So perfect. And then even if you want to see, I mean, there is training data, maybe you want to say, okay, print out just 2 records and truncate false, just to make sure, I mean, you have training and testing data as you expect. All right, great. So you can see that this is the data. All right, this is just for or sure that data is already there. So guys, everything's ready now, right? Ready for modeling. So what to model? We want to work with naive Bayes. So NB is going to be naive Bayes. All right. So you have to say feature columns. Where are you? Feature columns. So features column is going to be this scaled. This one, right? The scaled features. And then label column is going to be label. One thing here we need to take into consideration the smoothing. So guys, smoothing, as I described in the lecture, or Laplace, is used to handle scenarios where a particular feature is not present. All right, and then the probability would be 0. So we need to, I mean, work around on this smoothing. The best combination would be based on 0.0 and 1 usually, right? So let's say we want to take 0.5. All right, the default is 1. All right, but let's say we can take 0.5 because working with this, having try and error on this, you can get different outcomes for your classifier. So it means that you can have optimization on this because we are not still sure that which number is the best match, what is the best choice for the smoothing. All right, so let's take 0.5, right, as our initial step, right? Or maybe let's get just 1, which is the default one. Okay, just let's get 1. So mb.fit. So train data. All right. So, and then NB means naive Bayes. So predictions on the test, let's call it something like this. Please apply this model, transform it over test data. All right, just test data, guys, because train data, we don't need it to test accuracy because we want to apply accuracy on test data because test data is unseen data. We want to check this training data and this modeling is perfect, and we can use it and we can generalize it, you know, for testing data that we call them unseen data. So if you run this, all right, it's going to learn data, it's going to go through these probabilities and find you know, the classification as it is. So let's select this label, guys, just random stuff here, just label and prediction. What did you predict? So just let me say show 20 or say 25 records. Or I can say still trying to fit data, means still going to calculate those probabilities. Okay, it's done. So show 25 records, just to make sure we have this classifier. All right, can you see that label was 8, we predicted 2. So it means that here it was 8. 8 is here, right? Means 0, 1, 2, 3, 4, 5, 6, 7, 8. So it means that the original data was teardrop attack, but we wrongly predicted normal. So this is false prediction, right? So, but you can see that it was attack, but we detected normal. So you can see that 2 error here, but these are all correctly classified. Still wrong, wrong, wrong. Can see that these are wrong. We detect them all normal traffic. So you can see that, but these are good. But this is not really great measure to find it out. It's better to have this confusion matrix. So confusion matrix, please go over this test. All right, go over this and then group by label. All right, and this prediction and then count it. So let's name it confusion matrix or CM, and then this CM dot show. How many dot show in terms of the number of records that we are not sure how many there are, and truncate is false. Let me see. See that we had labeled 2, but we predicted 0. How many? 92 record. We had labeled 0, we predicted 8. How many record? 8 record. So this is the true classification. We had one label. I mean, the label was 1 and the prediction 1. How many? 31K. So, but here 0 is 8, right? And then 15 is 11 and so on. So here we cannot find that, you know, a binary classification matrix, true positive, false negative is, I mean, we can do that. I'm not saying we cannot do that. We can do it. But for multi-label classification, we would like to go ahead with, you know, the metrics that these are more feasible and frequently used for, you know, performance metrics. So now why not to visualize all this into the confusion matrix format? So open new cell and let's say that confusion matrix. All right, please get this CM, means this one, right? This is the CM. So then group by based on label. So group by label means that the indexes, the row would be labeled. We need the column now. We want to say pivot. Pivot means that shuffle or rotate or transform this table and take prediction as the column label. It means that this prediction, it's now the column label. All right, means 0 column label, 8 column label, 11 column label, 1 column label. And this 2 is row index, row index, row index. And please get this 92, 8, 2, 30 as the value on this transformation. So then prediction, then how the summation of, you know, the count. What is the count? It means, you know, this count. All right. So then if there is a null value that should be null value, okay, leave it. I'm going to explain what is this null value and then this show for me. All right, can see that. So label is here, means this is 8. So if we go over here, it says 8 is the label, prediction is 0. It says null. Why null? Because we don't have this combination 8 and 0. We don't have 8 and 0, 8 and 0. All right. So like 8 and 1, there are 50 records. All right. So let's find it out. So you can see that this one, 8 and 1, there are 50 reports. All right. So, and then you can see that here we can collect them all together into the tabular format. We need to avoid this null, and then it's much better to say NA, fill it with 0. And then you can uh, clearly see everything into the confusion matrix format. But in this confusion matrix format, it's highly recommended to avoid going through true positive, true negative, false positive, and false negative. That these are for binary classification. For multi-label classification, we use additional performance metrics like recall, precision, F1 score, Hamming, and log loss, many more. So you can see that label is 2. 2 is normal traffic. So, but we had it 92 detected as 0, 726 detected as 1. This is the true classification, but the rest and plus this is misclassification. All right, because the top is our prediction. This table is not complete, right? It means that we couldn't find the class 15, the label 15. We couldn't find any class to predict 15. So we might need to consider, let's just check, maybe here label count. No, it's correct. So you can see that here we don't have 15. All right, we don't have 15 here, right? So guys, it's obviously shows that this is smoothing. It's not really good one, not one. Let's take 0.5. All right, let me run with 0.5. So because let me run with 0.5 with 0.5. So with 0.5, so you can see that in the prediction we have just these ones as predicted. We don't have more than 13, right? This is really bad for classification. I just changed smoothing to 0.5 to see the result. Let's wait. So still, guys, it's not guaranteed to see other labels. All right, so you can see that now we have at least 2 more predicted labels. All right, this is the big difference. All right, you can see that how that smoothing is really important here. So let's go through this additional performance metrics. So before going through this Hamming loss and log loss, let's get back to those, frequently used ones that we can take them into multi-class classifier like accuracy, F1 score, prediction, precision, recall. Let's take them all, and then I will explain this Hamming and log loss. So let's call evaluator. All right, evaluator. I need this multi-class classification. That prediction column. Prediction column is prediction. All right, and then the label column is going to be label. That's it. All right. So now let's compute. So what to compute? Compute many stuff here. Let's just say accuracy. All right. Gonna be this evaluator dot evaluate. What to evaluate? This this NB. Where is it? This NB prediction test. This one. All right. So, and then you have to mention what is your metric for this evaluation. Evaluator dot metric name, all right, is going to be accuracy. You have to provide it as a dictionary format. Just let me double check. All right, so how many? Let me say it's 6. 1, 2, 3, 4, 5, 6. So second one, let's name it F1 score. All right, third one, let's call it precision. This one, let's say recall. This one, let's call it Hamming loss, and this one log loss, something like this. So let's check this one. So accuracy here should be F1. This one should be precision, but you have to add this one also by label. All right, we need to take this one. This is the keyword have been used. So recall by label. So here you have to say Hamming loss, and this one is going to be, you know, log loss. All right, so then you can print result. You would say that print accuracy. All right, and then we can round it. What to round this accuracy with 5 decimal point and then multiply by 100. You can copy this one, 2, 3, 4, 5, and 6. So this one, F1 score, this one, precision, right? This one, recall, this one, Hamming, and this one, you know, log loss. So make sure to remove this round here. All right, this is log. All right, and this is, you know, Hamming. This one is recall. This one is precision. This one is F1 score. All right, let's run these and then let me explain what these are. So Hamming loss, guys, you can use these additional metrics to check the accuracy, or let's say the goodness and robustness of your classifier. So Hamming loss is a metric used for multi-label. It measures the fraction of labels that are incorrectly predicted. You can see that 1 divided by the number of samples multiplied by the number of labels. All right. The combination of those predictions that they are not, is called that are incorrectly predicted. Okay, so it means that the ideal value of Hamming is 0, indicating perfect prediction. All right, we would like to get it 0, right? It means that we have a perfect, you know, prediction. For log loss, also we consider this log loss in the logistic regression lesson, and we call it also cross entropy loss, that we usually use it for binary classification. All right, so how does it work? It measures the performance of a classifier that outputs probabilities by quantifying the difference between predicted probability and true label. All right, you need to calculate the log. How does it work? If the label is 1, it means that this side is going to be 0, because 1 subtract by 1 is 0, is gone, and this one left, this one is remaining. It's going to be 1, and then multiply by log the probability that you calculated probability based on the logistic regression, for instance, and then you can find out, and then you can penalize the confident and incorrect prediction. The idea is log loss, the best result, perfect result means log loss is 0. It means that for log loss and for Hamming loss, we would like to get the performance metrics close to 0. So what you can see, accuracy 95, F1, 97, 97, 97, 99, 99. It seems it's okay. You might need, unless you might need to improve this 97%. Hamming and log loss. So we would like to get them close to 0. It seems this Hamming is very close to 0, but log loss not very close to 0 comparing to Hamming. But we need to improve this result. How to improve this result? You need to get a performance. Let's say you need to get an attribute that you need to play around with values to make sure that you can get better result, like smoothing in this case. All right, let's say that you want to get a smoothing, you want to apply, you want to get, different values here. All right, because the other labels, they are constant. Sorry, the other attributes, they are constant. This is the only attribute that you can change the value and then see how you can improve the result. So if we come back here, you can use optimization, two type of optimization, grid search and random search we want to apply. So guys, we have different techniques for optimization. Grid search and random search, these are, you know, commonly used ones. So grid search means that if you have 10 possible solutions, it's going to go over each 10 possible solution and find the best result. Time consuming, really. All right. Random search means that let's keep those 10 possible solutions and randomly take 3 or 4 or 2 or 5, you know, and then find how does it work. Let's apply both. In this case, we need these two, I mean, packages. And for grid search, let's see how we can do it. So if you want to do it, first of all, you need to get, you know, this naive Bayes. All right, naive Bayes. You have to say that this feature column, this features column, all right, should be this scale features. All right, and then, you know, the label column, label. So you can see that here I didn't mention smoothing. All right, I didn't mention. So let's name it NB. All right, so now here I have to say define the parameter grid. All right, for hyper parameter tuning. So guys, these hyperparameter tuning in this case is smoothing, means the attribute that you have to define it beforehand before running the model, right? So here I want to say that param grid is going to be this param grid builder. All right, so go to next line by using, you know, this backslash and then dot add grid. So what you have to add, so here you have to say those parameter. NB means, guys, this NB. All right, dot smoothing, because the smoothing is missing here. We want to find the best combination, the best value. So we want to go through a range of value, like say 0.1, 0.15, because we are not sure which one is the best one, right? Let's say 2, let's say 27, maybe 30, maybe 33, let's say 4.4, you know, 48. Guys, I basically do it really randomly, right? 50, maybe just go over 60. Sorry, 0.6, 60%, all right, and 70%, 72%. Maybe you want to also consider 76%, 0.8, 0.9, and let's say, and then 1. Or maybe here you want to also consider, you know, point. Let's consider all this stuff together. All right. So, and then please backslash and then say dot build. Okay, build this model for me. So define the evaluator. So based on what evaluator you want to consider, which smoothing is going to provide better results. So let's say that out of this evaluator, let me get this one. All right. Okay, so then here, let me get metric name accuracy. So guys, this metric name, we took it out here separately, right? Because we tried to go through different metrics, all right? But here I just want to consider based on one metric, accuracy. All right, so define, let's say define the cross validator. So what is this cross validator? Let me do it here, this cross validator. All right, cross validator is going to be cross validator. All right, so, and then let me add these parameters. Estimator is going to be this NB, right? That we have it here, and then estimator param maps. You have to say this param would be the inputs, all right? So comma, and then the evaluator. How to evaluate it? Evaluator here is going to be this evaluator, all right? And number of folds. I'm going to explain what is this. What is this cross validator? So cross validator performs a systematic evaluation of different combination of hyperparameters by dividing dataset into multiple subsets. We call it folds. Guys, how does it work? Let's say that you have, you have this data. Let's say this is your all data. Oh, sorry, guys. Let's say this is all data, or maybe let me change the color. This is data. All right, this is the entire data. All right, so then you had this training 70% and testing, right? This is testing and this is training, right? It was 70%, it was 30%, right? So then cross fold, here we said fold is 5. Fold is 5 means that you have to have your data into 5 folds, 3, 4, and 5. All right, you have to split your data, fairly to 5 fold, right? We call it fold 1, fold 2, fold 3, fold 4, and fold 5. You get one fold as a validator, okay? We call it validator. Validator means that run this, this naive Bayes, all right, over these 4, run over these 4, and then check the accuracy using this validator. So this validator is like a testing data, but this testing data is while, let's say is during training, while you do training. All right, so then you have to do the second fold. The second fold means that you have to move this validator, all right, into other folds. Means that have another fold, you can keep the same fold. Now this one is the validator. Then run this, naive Bayes over these 4 folds, all right, for training, and then check the result, check the accuracy over this fold, all right. If this one took best result, keep it as the best model, all right. But if this take a best result, get the second one as the best model, all right. And then you need to keep going, all right, keep going. The third one, whenever you could distribute this, you could distribute this folds, all right. It means that in this case, since we have 5 folds, you have 5 runs, all right. And then the third step, run this one, and then check the result over this, okay? Because testing, this stage, is for after training, all right? But validation is within training, all right? And then over these 5, let's say that this one provide better result in terms of accuracy, all right? Then keep it as the best model, all right? Keep it as the best model. So in this case, it says that have 5 fold, right? As we did here, all right? And then at each fold, take this one. Okay, how many? Let's say there are 10 combination, all right? Let's calculate the 10 combination. Let's say here we have 10 combination, all right? This 10 combination. Use these 10 combination and go over this and run them one by one and see which combination is going to give you better result. Let's say with combination, point might be 6 is going to be better result. Do the same thing for this. Maybe the best result is gonna be by 0.71. All right, and then you do over this, and then might be 0.3 is gonna be the best value, right, for the smoothing. But maybe over this 3, this middle one is the best. All right, and then you can take this one exactly for final modeling. So then let's continue. Then train the models. How to train? Let's say CV models for CV model. This cross validator is going to be cross validator fit. All right, train data. All right, it means get train data to run these for me. All right, and then get the best model. Okay, go over this, you guys. It takes time. It should take time, and then we should be very patient on this. All right, CV model, not best model, please, to see which one is the best combination. So make prediction. So how to make prediction? I want to say that predictions is going to be this best model, and then transform it now. Test data. All right, test data is for after modeling, after training. All right, so then evaluate. What to evaluate? Let's say accuracy, right? Accuracy. Evaluator dot evaluate. Evaluate. What to evaluate? This prediction. Not wrong. Yes, evaluate this prediction. So, and then get the best smoothing. Still, we are not sure which one was the best value. Okay, if you want to find it, let's say best smoothing is going to be best model, please dot get get or default smoothing. Why smoothing, guys? Because here we said smoothing. All right, whatever you have been written here, you have to add it here, right? And that's it, right? Let's print. Let's say best smoothing value, and then here you would say this best smoothing. All right, and then print accuracy. Let's do it without round. Okay, accuracy. Okay, I'm going to copy, guys, all this stuff. Control C. I mean, from this cell, right? And I want to run this. Okay, it's running. It's going to go over the loop. I want to paste here. Random means that you need to pick up a few values. I'm not going to run over all this. So what does it mean? It means that in this case, all right, we don't need cross validator. We don't need this one. All right, let me do something like this, but let me keep, this one as it is. Let me keep this one. All right, let me drop all this stuff. All right, before training. All right, what we have to do, or maybe let me do one more thing. Let me get back to this. Let me keep this evaluator. We need this evaluator, but we don't need the rest. Okay, let me keep evaluator. And then here, I want to say that perform random search manually, guys. How? I want to say that the best accuracy, we want to get like 0. All right, because we want to increase it. And best param, that is going to be the smoothing. Let's say none. Still, we are not sure what is the best value for a smoothing. All right, so then here I'll have to say, because it's going to be manually, for smoothing in this one, right? But guys, we are not going to do it all. We have to select a few of them. It means that here, come over here and then say import random import random, and then come over here and then say random.sample. Out of this, please select, maybe you want to try by 5 of them. Go through this, select 5 values randomly, and then go through these steps. What are the steps? This one, let me cut this one. All right. This is the MB and smoothing. So guys, can see that we do it manually. Smoothing is this is smoothing. And the model is going to be nb.fit. All right, train data, guys. So, and then you need to remove this too and keep working with the rest. Just let me make sure this is not best model. Let's say model, transform it over test data, and then here check the accuracy, and then so guys, make sure to keep everything inside the loop. All right, make sure to keep inside the loop. It means that here, model it, check the prediction, check the accuracy. All right, afterwards here, you have to check. So means that remove this one, and here says that check if the current model is the best so far. All right, how we have to check if this accuracy, right, is better than best accuracy. Where is this best accuracy, guys? It's here, right? This one. What to do? This best accuracy is going to be the current accuracy. And what about this best param? This best param is going to be the current smoothing, this one. All right, that's it. This is for manual one. And let me run this manual one also. So guys can see that this one is still working. So because it's going to test the model, go through the model over these combinations, and it takes time. All right. So this is to let's call them like basic to intermediate optimization techniques, but we have meta heuristic algorithm if you are interested in. We have a Bayesian optimization that we can use for, you know, for optimization purposes. But these are still, you know, the valid optimization techniques, grid search and random search. Still grid search is going on. Let's see what is the best combination. So here we achieve 97.4. All right, 97.04, you know, for the accuracy we could collect it. And then what we did here, we had this, you know, combination with smoothing 0.5. All right, let's see what is the best smoothing value. So still grid search is going on, and still here fit, because many consideration there are. All right, it's done. So all right, so consider still 0.5 is the best result. All right, 0.97.4. So guys, I basically I really selected this smoothing by chance, 0.5. I didn't know that this is the best one. I really didn't know it. This is the best one. So by the way, if you tried with one that was the, I mean, that was the original one, the default one. So it's not the, I mean, the optimized one. I mean, if you want to go ahead with number one, which is the default one, it's not optimized solution. Optimized solution is whenever you have 0.5. So 0.5, you know, out of this. If you might, who knows, if you add 0.55, maybe that's gonna to be really the best one. Maybe 57.7 is the best one. So guys, you can see that is a bit challenging. How to find it out? Advanced optimization techniques like meta-heuristic optimization techniques. You can take it for your self-study if you wish to know more. So random search is now running. You can see that cursor is here. It's going to go through this list, but we selected 5 randomly. All right. If you can also take this one, and then maybe after the result you can paste it here. All right, just skip it. We can run it, and then you can see that at each run you have 5 different combination. So it's still running. You can see that accuracy check. So if you have this only 2 cores available on Google Colab, I highly recommend you to go ahead with the 10% of data size because of time consuming process that you can see is running here. If you have much better hardware, more than 2 cores, if you have at least 8 cores, and then yeah, you can go ahead with the largest file. All right, done. So guys, still it says 0.5 after going through this, still 0.5 is the best result. So if I run this, you can see that in this combination took this one. If I run again, you can see that combination change, but we are lucky that 0.5 is still there, right? You can see that it's still there, but third time is not there. But just imagine if you run this one again, all right, it might facing with the combination without 0.5, and then you know that the accuracy will be changed. All right, guys, I hope you enjoyed this topic. Gaussian Naive Bayes, very strong technique for classification, and also you enjoyed these optimization steps. See you next tutorial.